Hello, good morning, good evening, good afternoon, everybody, wherever you might be. Most importantly, bom dia, Brazil. We are very happy to have a speaker from Florianópolis, also known as Floripa. And he will treat us to local bisections of Hopf algebroids and inverse semigroups. ELIEZER, it's all yours. Take it away.
Okay, thank you very much for this invitation. I am very glad to participate of this North Atlantic non-commutative geometry seminar, and I will talk about.
Despite being at South Atlantic, right? You don't mind that it's North Atlantic and you are at South Atlantic. Okay.
Okay, and while I am presenting, I will not see you anymore. But if you have some questions, you can only ask, and then I can hear you, all of
Okay.
you.
Okay.
Then this work is joint work with Paolo Saraco, formerly from Brussels University and now from Sevilla University. And then I will try to show what we are doing. It's a ongoing work, then it's not totally finished, but there are some very nice results here. Let me start with an outline. I will talk about local bisections in groupoids, and how this is quite old. In fact, I think there are at least 10 years the results I will talk in this first part, and then jump for local biretractions on commutative Hopf algebroids. I will call it biretractions because all the arrows will be reversed in that context. Then instead of bisections, there will be biretractions. I will explain lately. And then I will show that there is a functorial construction between the category of Hopf algebroids with some specific morphisms and the category of inverse semigroups. And then I will construct this functor, and then in the end, present some perspectives, some things which are we are stuck in at the moment. We are trying to find some ways and what we want to do in the future about this topic. Okay, let us see. Then I will start with this work with of 2012 and of Alcides Bus, Rui Excel, and Ralph Meyer, uh, when they construct semigroup actions, inverse semigroup actions as groupoid actions. And then let me change the color. Uh, okay, and then what is the construction of there? From étale groupoids, they construct a functor from the category of étale groupoids with some morphisms I will explain later, which is the inverse same group of bisections of a groupoid. Then each groupoid gives rise to an inverse same group of bisections. And then in the other direction, they have a functor from inverse semigroup to the groupoid of germs of actions of this inverse semigroup. Then this is in fact an adjunction. This germ groupoid functor is a left adjoint of the functor of bisections. Then I will explain more or less the lower part, this functor, and then go to our context. Instead of groupoids, we are going to commutative Hopf algebroids and construct a functor more or less in the same steps as this functor groupoids. And then we go to explain why this germ groupoid or is more difficult to translate into the context of Hopf algebroids. This is my aim of this for this talk. Okay, let us go. Then let us start with a local bisection of a groupoid. In the first definition I will give is basically a subset of the groupoid such that restricted to that the map source and target are injective. Then more or less we could see, let me draw.
Tomek, Eliezer said that you should just ask a question
Okay.
because he doesn't see you on screen.
Sorry, I missed
Okay.
it. I have a question to the previous slide. When you have this adjunction, these two functors, could you come back to the previous slide for a while?
Okay, let me go. Yes.
Okay, so my question is, what are subcategories of étale groupoids and inverse semigroups for which this adjunction defines an equivalence? What can be said about such étale groupoids and such inverse semigroups?
Well, in fact, we will see that for groupoids with algebraic morphisms, you can construct this functor of bisections. I think when you restrict it to étale, at least from one side, if you start with a groupoid étale, then you construct the inverse semigroup of bisections of this group. This is an inverse semigroup, and then construct the germ groupoid of this bisection. This acts on a specific set. Then these two. This is again an étale. Uh, I think when you put étale groupoids here is already the equivalent of the because the semigroup acts on the character space of the units of the semigroup. I will explain later how we construct this, and then you construct the bisections of GS. I think for étale you can have an isomorphism here. I think, okay, when you put étale groupoids, this, I think it's a categorical equivalence. You can have these two things, but I'm not totally sure. But in fact, as I will explain, if I take only groupoids with some morphism, I can construct this functor from bisections from the category of groupoids, and then it's only it will be only an adjunction.
Just to make a comment here, there's the work by Pedro Rezende, then later by Lawson, Lawson and Lenz, where they use the pseudogroups, an abstract version of pseudogroup, then they have an equivalence between étale groupoids and pseudogroups. So you need more structure than only the inverse semigroups.
Okay, I see.
They changed the work of Rezende and Lawson Lenz considers different morphisms though.
Yeah.
For the étale groupoids. And also the construction by Bus, Excel, Meyer, you don't, if I'm not mistaken, you don't get the original groupoid back if you pass through this, except maybe if it's discrete. No, not even that, because the way they construct the character space adds a lot of extra points. So you always end up with a bigger groupoid, almost always.
Okay, thank you for the contribution of Gilles and Jonathan. Okay, let me go back to...
Okay, thank
you. Okay, then more or less is, if you take, this is G0, and then this is G, basically is a subset, and then it's more or less, I can see it as a section, such that the source and the target is injective. Let me change the color. Both the source and the target restricted to that subset is is injected. In fact, there is a very nice metaphor about this. If you consider the set of objects of your groupoid as a lake, then each morphism, and take a part of this lake, a subset X, and then take any morphism starting from this, like a fish jumping from that part, jumping from the lake from that part. And then we can consider that subset, then those fishes are in fact morphisms belonging to the groupoid, whose source and target source is the point where it emerges from the water, and the target, the point where it plunges to the water. And then if we take several fishes uh, jumping parallel in a parallel form, then it would be more or less what we can, how can we can imagine the bisection of a groupoid, this set of fishes jumping in a parallel form from this X to another subset, and then every morphism has its source in X and its target in Y. Then this is more or less how I can imagine pictorially what a bisection of a groupoid is. Okay, let me go. Um, yes, for étale groupoids are important because they are topological groupoids which the source and target maps are local homeomorphisms. Then, for these groupoids, the set of open bisections, if you take open bisections, not any bisection, but only open, they constitute a basis for the topology of the whole groupoid. Then you can have a basis of open bisections. Then this is the importance, because the bisections in an étale groupoid are more controllable topologically. And for ample groupoids are étale groupoids which admits a basis of compact open subsets. And then you can have a basis of compact open bisections in an ample groupoid. In what I will talk from here, I will more or less forget topological issues about the groupoid. I will concentrate only in the algebraic uh, algebraic aspects of the groupoid, and then trying to go in that direction. Then, for our purpose, I have to um, two bisections in that definitions, two subsets of the groupoid, such that the source and target are injective. They can be multiplied. You can multiply two bisections, taking the uh, products in the groupoid of elements of the U and V, such that they can be composed. Only the composable pairs are present here, and then this is the product. And you can define a pseudo inverse, and then this forms a inverse semigroup. That, let me see. Yes, that then this product is associative, and then it for each bisection U, you have a unique bisection U star, so that these two relations can be done. And by construction, you can see that the pseudo inverse is uniquely determined, and then it's more than a regular semigroup, is an inverse semigroup. And which are the idempotents of this set of bisections is the idempotent is only a subset of the set of units of this groupoid. Then these are in fact the uh, idempotents in this inverse semigroup. Okay, then from the groupoid you can construct, then groupoid you can construct the inverse semigroup of bisections of then this is a groupoid. This is inverse semigroup. Okay, then let us go. Let us do a small modification in the definition, because we are going to the to approach these bisections to Hopf algebroids, and then we have to have maps instead of subsets in order to modify the to reverse the arrows to speak about Hopf algebroids. And then I will define a local bisection of a groupoid as a pair consisting in a subset of the set of units of the groupoid, and a map from this subset to the groupoid such that two axioms are done. If you do this map and then apply the source, you go to the identity. Then this U is more or less a section of the source map. As the source map is, then you are taking only a small piece of the whole groupoid.
It's his internet.
G. Bisection is a bijective map between X.
It's funny, he's frozen, but ELIEZER, you are frozen. Hello, ELIEZER, you are frozen.
X here you. Sorry.
You were frozen for like 1 minute at
Sorry.
least.
Oh my God.
I can hear you.
We can hear you now.
Yeah. But he was frozen. Yeah. Now we can hear you as well. Yes.
Sorry. Let me see. Okay. Okay. Then can you say me in which part you lost me?
We lost you when you were starting drawing these circles.
Okay. Then let me. Okay. Then the source. Let me put another version of this. This is G0. This is X, and then this is G. You have U, and if you have the source, you go back to the same set. This is the first axiom. But if you take the target, you go to target U of X. This is another subset of G0, and then these are in bijection. This is our version of what a local bisection is. Then the set of these bisections is an inverse semigroup. We can multiply two bisections, giving a third bisection. And if we start with a domain X and a domain Y, how do you construct the domain Z? Let us see here that X and then the tau U This is tau u of x. And then this is, let me modify the color. This is y. This is tau v. Y, but in fact, they are, here we have a u going from x to g, and you have a v going to from y to g. Then the domain of the composition is basically the pre-image of this intersection. Then there's this intersection here, and you take the pre-image of this intersection by target composed with u. Then this pre-image is the domain of the composition. This is what is described by that z. And what is the convolution product of um, uh, these two local bisection? In a point x, if you take x here, point x here, then it will be u on x multiplied in the groupoid. This is the multiplication in the groupoid. U of x, which is an element of the groupoid, with v in, this is the point tau of u of x, and then v calculated in that point, and you multiply both in the groupoid. This is what is this new element of the groupoid calculated on x. And you can have as well a pseudo inverse. Let me, it is, let me see whether I can put here x. Then the domain of the pseudo inverse is that codomain of u, and then the tau of u. Then this is the u, the target composed with u, and then this is the bisection. Then you take an element here, and what is that bisection in that point tau of u of x is simply the inverse of u of x. Then u of x is this u of x can be seen as this element of the groupoid whose source is this and target is this. Then you take the inverse of this element of the groupoid, and this becomes an inverse semigroup as well. This multiplication is associative. This is in fact a pseudo inverse. Then you can see that you can ux with ux star, ux is equal to ux, and otherwise if you put stars in the points and ux in the middle, then it is equal to ux star, and it is uniquely determined, and then this is in fact an inverse semigroup in that context. And this is more appropriate to dualize for the context of Hopf algebroid. Then let us start for what are commutative Hopf algebroid. Então, so a commutative Hopf algebroid is a pair of commutative algebras H and A together with those algebra morphisms, source and target from A to H, epsilon from H to A, S from H to H, which is the antipode, and delta is a commultiplication from H to H tensor H based on A. And what? If you take the H the delta and epsilon, this is an A ring with but A ring, you need to be an A bimodule, and the A bimodule structure is given by the map source and target like this. In fact, as here everything is commutative, doesn't matter the side where we put the source and target, but I will put as it was if it was non-commutative, only to see that we are using the right bialgebroid structure in that context. And then what more? The source, the antipode intertwines the source and target maps, and it is involutive. And here we have the axiom of the antipode as in a Hopf algebroid, and then in Swidler notation, we can write the co-multiplication as this. Then what is happening in the axiom tree is basically this in terms of elements. I will use more the notation in terms of elements than in the terms of composition of maps. But I will, in certain points, I will exchange the two notations, compositions or in elements, and I will use both. Okay. Examples, simple examples. For example, if you take a commutative algebra A, then the tensor product A tensor A is a commutative Hopf algebroid with this source and this target and this delta, this co-multiplication, and this epsilon, and this antipode. Antipode only intertwines is the flip map, intertwines the positions of the first and the second entry in the tensor product. And if
So
you
this is like ELIEZER. So this is like pair groupoid, right?
Yes, this is basically pair groupoid. You can do a bit more sophisticated version, taking the Laurent polynomials based on this pair, this tensor product algebra. Then the coefficients are in the tensor product, but you can have Laurent polynomials, and then the only differences is in the co-multiplication that this generator X is group-like, as you can see here, and the antipode basically gives the inverse of this X up to the power n. The antipode is X to the power minus n. Then the only thing I think, and if you take the epsilon, you take only the zero part, n equals zero part, and all others are zero. You can not have contributions of this part to the epsilon. Okay, let us go to another example. I think the paradigmatic example is the affine groupoid scheme, which is a pair of functors from the category of commutative Hopf algebra to a set, such that you can have, if you call this G and this G0, and then if you take this pair, which is G of B, G0 of B, this is a groupoid. Then there is all the maps which defines a groupoid, the multiplication map, the source and target map in this groupoid, the unit map. And then if you reverse all the arrows, you can see that the pair HA determines a commutative Hopf algebroid according to that definition I have already done. Then this, I think it's a paradigmatic example, in fact, to give the ideas how to construct the corresponding notions in the context of commutative Hopf algebroids. Then this will be important. Okay, let me see. Then I will present two different versions of local biretractions of commutative Hopf algebroids. The first version was published in my paper with Marcelo Alves and Franciele Kurtenboing, quantum inverse semigroups. In this paper, we defined a local biretraction of a commutative Hopf algebroid as a multiplicative linear k-linear map. Is not it is important multiplicatively a k-linear map, not an algebra map, because it doesn't take the unit into the unit of h into the unit of a. Then this guy, alpha of 1 of h, is only an idempotent. And then we put these two conditions. Alpha composed with the source of an element of A is basically multiplying A by alpha of 1. This is more or less saying that the source projects into the image of alpha and basically gives this projection. And the second is the existence of an element of A such that alpha tensor T, alpha composed with the target of E alpha, gives this idempotent alpha of 1, and this map alpha composed with the target restricted to this ideal gives a bijection with the other ideal. Bijection, and here is an algebra map, because if you consider E alpha as a unit of this ideal and alpha of 1 the unit of this ideal because of this relation, then this is in fact an algebra map and an algebra homomorphism, isomorphism between A E alpha and A alpha of 1. This I will tell you what is the problem with this definition. We could prove lots of things about this. For example, the elements alpha of 1 and E alpha are in fact idempotents, and once defined the map alpha, the element E alpha is uniquely determined. Then we don't need define as a pair alpha E alpha, because this comes for free from the definition of alpha and the other conditions. Then each map alpha gives rise only to only one idempotent E alpha. Then you don't need define as a pair. And in fact, the image of alpha is in fact this ideal A generated by alpha of 1. And then this, again, alpha of 1 is an idempotent, and everything is commutative, then is a central idempotent, then this is in fact an ideal in the whole algebra A. And then, and more or less making pictures, when you started in the groupoid X and then take a target composed with U, you give an bijection to this set. Here the arrows are inversed, and then instead of this X, basically we have the image of alpha, which is the ideal generated by alpha of 1. And basically this is like a black hole. When you come here, you don't escape anymore. But and then to make sense of this arrow, which goes in the opposite direction, this is alpha composed with target, then you started with this another ideal of A, and then this is an isomorphism of ideals, and then goes in that opposite direction. More or less, this is my pictorial view of what happens here in that definition. But if you define this, the set of B retractions, and then I call B retractions instead of bisection because goes in the opposite direction. Bisection.
But Google tried to change this by retraction into bid retraction.
Ah.
So you have to be careful with spell checking.
No, this just means we have to make biretraction so popular that Google now recognizes it.
Absolutely, yes. My point exactly.
Now, bisection goes from X to the groupoid, and by retraction goes from the whole Hopf algebroid to the base algebra. And then here, if you take the source, then it is in fact a section of source, and because of that bijection with T composed with U, then it is a section of the target as well. And here, if you take the source first and target, then you restrict it to sorry, this is alpha, and then you restrict it to that image of alpha, and then more or less is a retraction of S, is not a local retraction of S. The S is the source of map which goes from all A to H, and then when you apply the alpha, you go into an ideal. Then this is more or less how I see why it's called biretraction. And it is, but one problem is you can prove that it is a regular monoid, not necessarily an inverse monoid. You can define a product, convolution product of two biretractions like this, and then you can identify which is the idempotent associated to this biretraction, which is that idempotent, and then the pseudo inverse as well. You have to use the antipode of the Hopf algebroid, and then the explicit bijective map alpha composed with the target. Then you have to use the inverse to construct that pseudo inverse, and the idempotent relative to the pseudo inverse is basically alpha of 1, the final idempotent of alpha. Then you go that the arrow go in the opposed direction as it was expected. But the problem is we tried to prove that we cannot prove even that alpha star is unique and or equivalent, that idempotents commute. And this we couldn't prove in this. In fact, we tried to prove that the idempotents commute, and then we saw that almost never it occurs. In fact, this is equivalent to prove that
You couldn't prove it because it wasn't true, right?
Yes, probably in some case we found some examples for those algebras, A tensor A. Then I think in those cases we took the semigroup of biretractions isomorphic to another semigroup, and I think those semigroups are inverse semigroups, not only regular semigroups. But I think in particular cases it is true, but not always true in general. Okay.
But may I ask, is in the global bisection or global biretraction, this is true, right?
In global, I think it's true because when it is global, the bisection, the biretractions, it's a group, not anymore an inverse semigroup. If you take the global ones, only the global biretractions, then it's a group structure, has a group structure for. Is shall
Yeah.
who's yes. Then now yes, you did this, and it's true that global biretractions of Hopf algebroid, they form a group. We are trying to take versions or localized versions, then to give rise to inverse semigroups, or at least regular semigroups.
So
But
that means what you call biretraction is what we call bisection. So we use a different word, but in your case, you most concentrate on the local case. Yeah. Okay.
yes.
So then I know how these two picture combined. Okay. Thank you, Evan.
Okay, let me go back. And but one thing, before one thing, because this it was in our paper of quantum inverse semigroups. And if we take one thing more, let me erase some things to have more space. If you take the algebra of this semigroup, this we could prove that it's a quantum inverse semigroup. Basically, the whole work, whole paper was about this new definition we are trying about the quantum inverse semigroup, which is, I hope, the true structure which would interact with Hopf algebroids in the same sense as inverse semigroups interact with groupoids. We started that work was the starting point, and then I think there is a long road to establish all the correspondence between quantum inverse semigroups and Hopf algebroids in general. But in this case,
you are talking about a non-commutative generalization of étale groupoids. Otherwise, for instance, if you have an algebraic groupoid, then you can have very few idempotents inside. So your inverse semigroup would be very poor. So you are trying to generalize the situation of étale groupoids to the non-commutative setting.
Yes, in fact, what I have to say sincerely, I don't know yet how to put all those topological issues in terms of our algebraic setting. We are more or less touching the things in a dark room and trying to figure out what is happening. Okay, but I think this is a good program to follow, because in fact Hopf algebroids arose in a sense that they are the generalization of groupoids for the Hopf algebraic world. And then I think all the relationship between groupoids and inverse semigroups in that in our setting has to be translated in the other side. But then what I constructed was that notion of quantum inverse semigroup, which was in certain sense like that play of Pirandello, 6 characters in search of an author. Then basically we had some examples I would like to be quantum inverse semigroups, and then I created that notion in order to those examples I would like to be should fit into that context. Then this is how quantum inverse semigroups arose. Then Hopf algebras, weak Hopf algebras, algebras of inverse semigroups, algebras of Hopf categories, everything fit into the context of quantum inverse semigroup. But then it is a baby concept yet.
Yeah, I'm insisting only on to keep in mind that we are talking about étale situation.
Yeah, yes,
Otherwise,
I know that I live in a context here in Florianópolis, and where everybody talks about the Algebroids all the time, and then Algebroid, I know that importance of Algebroid.
okay.
Okay, let me go further more. Then the new approach, which is basically here, starts my work with Paolo. This approach appeared first in 2022 when we started to discuss. And then instead of considering idempotents, because in fact idempotents are very few in certain sense, we started to see, for example, when you have in algebraic geometry, you have a subset like this is R and this is X, then in general you associate to this subset an ideal of polynomial such that P of points A here are zero for all A into that subset. And then the algebra of functions on X basically is the polynomial, at least for algebraic, divided by quotiented by this ideal. Then this is more or less the approach we started to follow in the definition. Then a biretraction, a local biretraction, should be a pair of a map and an ideal of the base algebra, and a map going from the Hopf algebroid into a quotient of the base algebra, such that the composition with the source is the projection upon this quotient, is the projection map, and the composition of the biretraction with the target is surjective upon the same is a surjective map upon the same quotient. Then this is basically the two conditions we ask about this alpha. Okay.
ELIEZER, I don't want to distract you, but you want pink. I mean, you are pink.
No, this I think this is a problem of my camera of my computer. It has occurred before, and I am not worried
Okay.
about.
Okay, if you are not
anymore.
worried, I'm happy.
Not really pink.
I love Pink Floyd, so for me, pink is okay.
But the screen I am sharing is okay.
It's white. Yeah, it's
okay.
white. Yes.
Not pink.
Not
Okay,
pink.
then it was my concern, but then okay. Okay, the convolution.
Sorry, I have a question.
Okay.
I have a question about your name. You are calling it closed local biretraction.
Yeah, the closed because in fact when we consider ideals, we are relating ideals of the polynomial algebra to a closed subset. This is more or less how we relate ideals and subsets are related to closed subsets in certain sense. Then this disclosed only appeared in our, but it is in our paper here what we are trying to finish, and then but this is more or less like an intuition on how do we take this, is this intuition comes from algebraic geometry.
Yes, but please help me to understand the situation. For instance, in the topological groupoid case, local bisections, they form a base of topology. Okay, but this corresponds to the fact that there are in this topology there are clopens, they're closed and open subsets. So now you are insisting of preserving closedness, but you are giving up openness. So I wonder what would happen if you will restrict your construction to the commutative case.
Is this just because we're kind of sitting in the dual picture? And
no,
usually,
it's not.
Okay.
No, it's not duality. It's simply this ideal corresponds to a closed subset, but this closed subset is an open subset in the previous situation. So this means that it's closed and open. Okay, but then we had this in the case of the clopen, we have this relationship with idempotents, with projections. And now I cannot see these projections. So this situation sounds
yes, in
strange
fact,
to me.
No, I think some things can be more clarified. Thank you for your question, and I think we have to put it in a more appropriate form. I put closed only because I was preparing, and it was like as it was defined. But in fact, this word can cause some confusion in the some distraction in the whole process. What I'm saying that I will not talk about things topologically, at least in this talk. No, but I know that they are needed to be studied in more detail, and I think it is a good thing to reformulate in that definition. Perhaps not in definition, but at least to for example, if we are trying to go to ample, the ample groupoids, I think are the best one to treat them algebraically, because then the algebra of the groupoid is the Steinberg algebra, and then I think these are the most appropriate groupoids to have a laboratory of our constructions in the dual case. But this, I think this is not yet done at this moment.
So if I could comment a little bit about this. So in the case of algebraic geometry, if you are speaking about some open subset of an affine scheme, you are talking about localizations. You are not going to do this. If you are talking about the topological situation, you can speak about these functions of type C0 of some open subsets. So there are non-unital algebras. You are not going to do any of these versions. So in a sense, your biretractions are piecewise rather than local.
Yes.
So in the theory of principal bundles, there was a period when people tried to mimic local triviality, but they realized afterwards that they are speaking about piecewise triviality. So so your construction is an analog of this piecewise thing.
Okay.
Yes, and we prove that piecewise is different from local.
Yes, it's my point.
Thank you. Thank you very much for your considerations. I will have some we have to finish and to work on this work, and then I think there are lot of things to think about. Thank you very much again. Let us go at least what I have prepared here to have a more or less a bird's eye view on what is happening here. Okay, then this is the, well, that that word perhaps we have to be careful about. Local Bay action, then it's that pair of an ideal in this map satisfying these two conditions. Okay, and we have a convolution product of two birotation, and this is the important part, because it is there are lots of things to consider. I will try to give a hint on how to construct this ideal K upon the ideal I and J. Here we have two different projections. One projection from A to A over I given by Pi, and beta composed with tau, which is surjective as well. Both are surjective on A of G. If you take the I is an ideal of A, and take beta of T of I, this will be, it's easy to see that it is an ideal of A over J. But if it is an ideal of A over J, then by the correspondence theorem, there exists an ideal of A containing I relative such that B composed with T over I is basically this quotient. This is the correspondence. And then we can take this A over K and take the projection. I will call this projection Kj, then simply killing more people here. And then as I take this composition here, I is in the kernel, because effectively what comes from I here is killed when we quotient by K. Then you can transfer this morphism for, there exists a unique morphism from the quotient A over I to A over K, closing this diagram. And this diagram, in fact, is a push-out diagram in the category of commutative algebras. Then this K is basically given by this formula. And the convolution product, in how we define the convolution product, then this is what I prepared in the last transparency, in last slide. Sorry?
Sorry, ELIEZER, just a stupid question. Isn't K simply equal to I plus J?
Of course, this quotient is isomorphic in the category of commutative algebra. This will be is this basically is this space is isomorphic to this. This is in fact a push out in the category of commutative algebras, and then those things are related. In fact, this A over I tensor over A over J, perhaps K is I plus J.
Well, that's how it looks.
Okay.
So this is the question whether the Chinese remainder theorem holds in your category.
All right.
Yes. If it is, if I plus J would be the whole A. No. Sorry.
No, it's not the whole thing.
No. Okay, but then there exists this isomorphism, and this will be important in some in some point in the future. But I will I will emphasize here the convolution product about of these two big retractions calculated on an element H of the Hopf algebroid. Then you split into the co-multiplication, apply alpha in the first, beta in the second, and then project both into this quotient by phi, because this belongs to A over I, and then you apply phi to this belongs to A over K, and this beta belongs to A over J, and then you apply this projection for both belong to A over K, and then you can multiply in this quotient. This is the final result of this product A and alpha and beta applied on H. Then for every product, in fact, you have to draw your push out in order to see which is the correct correct ideal and which are the maps you are using to project into the same ideal in the same quotient in order to multiply both of them. Then this is a technical complication which appears in our approach, but this it's kind of...
This is like a construction of Z. This is very much like a construction of Z before.
Yes, indeed. That Z, in fact, good question, Piotr. Let me, because let me see whether I can, when you, let me go into the direction. In the groupoid case, you have the G0, then you have X, which injects into G0, and you have this is how to construct a UX product V Y I gave before, and then Y you can have by yes, tau V. In order, I apply this in order to inside here they have some intersection. Then basically I have to see the intersection of X with the TV of Y, but then I would like to have a pullback here. Then I would have to put the same maps here, TV. Then in fact the correct place is this. Then if I apply TV here, I end up into the intersection of X and this translation of Y. And if here and apply because TV minus 1 TV of Y, then it is injected on Y. Then this is the injection, and this is basically the a pullback. And this pullback is dual of this construction here, as Piotr emphasized last in the last speak of him. Okay.
But I'm confused about what you call pullback and what you call push out, because I would call it the other way around. This diagram of algebras would be a pullback.
Push
and
out,
diagram...
because push out here because it has an universal properties, an arrow coming from this. While pullbacks, the universal is a universal arrow from a pullback. For a pullback is an arrow coming into it. Then this is a push out.
No, Tomek, do you agree? I don't agree.
Yes, I agree. It's about a generalization of an intersection of two open subsets. It's not gluing along a common intersection. So I think I understand Piotr's objection. or confusion. Yeah. But I think it's everything okay, because you are talking about something which analyzes the intersection of two open subsets. It's not a gluing of two spaces along the common intersection.
Okay. Okay. Thank you, Tom.
Okay, let us move further. How long I have yet?
You have 25 minutes.
25. I think it's okay. Okay, this is the convolution product, and then we can see that the convolution product is a biretraction. For example, we have to prove that the composition with the source is the projection on the correct, and this can be seen because the 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 commultiplication of the source is one tensor source. Then going back to the, I will write here to see alpha beta on H is phi of alpha H1 P K J beta of H2. Then if I take for source, then one phi of alpha of one, but those things are algebra map. Then this is basically the class of one in A over K, and pkj of beta of but beta of source is pi j, and this composition of pi kj pi j is simply the projection over K. You project before over A over J, and then project on from A over J to A over K, then you project directly for A over K. Then this is the thing. And for composition with the target, then the target, the delta of the target goes into the first leg of the tensor product. Then it's phi alpha target pkj. This is the unit of AK, and this composition alpha t is surjective, and phi because it is a push out, this is surjective, then this is a push out, then we can prove that this is surjective as well. Then everything is surjective, and then the second axiom of biretraction is okay as well. And this datum, you can prove that what is this? This epsilon is the co-unit of, and the ideal is only the zero ideal, and then this is basically I am writing like this, and this is a biretraction because epsilon composed with S is identity on A, as epsilon composed with target is our identity of A as well. And then this is a biretraction, and if you take, for example, alpha with epsilon, then goes to, this is the unit of the monoid. This is something easy to recognize. But the hardest part is the associativity, because in the associativity you have to consider this composition AI, beta J, alpha I, beta J, and gamma L, and then go the first two, then you have that K, that ideal K, and then go into another, that K and L forms another ideal by this push-out diagram here. But on the other hand, you have this, if you compose the two, then you have a new ideal N given by this push out, and then making this two, you have finally this ideal given by the second push out. And then there is a lot, this basically in our writings is a 3-page long proof to see that this ideal P and this ideal M, they coincide, and those alpha star beta gamma on H would be the same as alpha beta gamma on H. This is quite technical when lots of universal property of push-outs involved to show this part. Then I give only a hint of how we could do this in fact, but then we can prove that it's a monoid, and more we can define a pseudo inverse of a alpha I, which is the ideal associated to the pseudo inverse is the kernel of alpha composed with tau, and this is the inverse. Again, it uses the antipode, and there is this phi alpha, which is bijective here. It is you use the inverse of you have to prove that surjective is okay, but it is of course alpha t, then k alpha is exactly the kernel, then you are quotienting by the kernel, then it is injective as well. Then this phi alpha is bijective, and you use the inverse of this. Then you can see that, for example, alpha star alpha is alpha, and alpha star alpha star is alpha star, and the uniqueness of the pseudo inverse, this is the hardest part of that proof, because this is what we couldn't do with the approach with idempotents, but with this approach with ideals and quotients, then it is true that we have a unique pseudo inverse for each element, and then it is an inverse semigroup. And then the theorem is that this data constitute an inverse monoid more than an inverse semigroup, because we have the unit given by the epsilon and the pseudo inverse given by this dagger.
Sorry, I just wanted to double check. When you speak about these two different approaches, are they equivalent or are they different?
What I proved is that if we start with the approach with idempotent, I think it's the next slide. Let us see.
Okay.
Yes, if alpha is a biretraction of the first kind, which is given by those idempotents, then you can see that there exists an ideal and an algebra morphism between H and the quotient of this ideal, such that this new this map and this ideal is a biretraction of the second kind that I presented, but not on the contrary. Not every morphism biretraction of the second kind is of the first kind. That's why there is a point when we can see clearly why you can, in fact, have a uniqueness of a pseudo inverse in the second kind, but you don't have, you cannot prove in general the uniqueness of pseudo inverse in the first kind.
All clear. Yeah. Thank you.
Okay, then let's go for a construction of a functor. This construction of biretraction is functorial. let's go back to what happens in terms of groupoids. I will define an algebraic morphism between two groupoids. These are groupoids. Is an action of the first groupoid into the set of arrows of the second groupoid commuting with the regular action. Then you have basically the action here, and then you have, well, in fact, you can erase, in fact, this H1 because even the objects you can see as arrows, and then basically you have here G0, you will have an anchor map row, and you have this action. Let me go this action with me, and this action is going by the multiplication, and here basically you have the source map here, and then these two actions commute. Basically, it is what I said, that there is a map from the H to the set of objects of G, and this action from G upon H, I will denote only by this, subject to these conditions. For example, this row, if I take two elements in two composable elements in H, the anchor map of their product is the anchor map applied on the first. Then more or less this is saying that the action of G doesn't see the right multiplication by H. And if you take the anchor map after acting, is basically taking the target of this element of G who acted. This is, of course, naturally in actions. This as well is common in the definition of an action of G upon H, and the unit of the anchor map acting on H is the identity on H, and if I take an element of G acting on a product, it acts only on the first. And this axiom and this axiom basically are saying that the action of G commutes with the right action of H by multiplication. Basically, this is...
Sorry, Eliezer, just a notational question. You have these symbols, superscripts with 2 in parentheses. Does it mean just the second Cartesian product,
yes,
or does it mean something smaller?
This is... such that source of H1 is equal to target of H2.
Also composable. Okay.
Yes.
Thank you.
Okay, and this morphism can define a category. You can compose those two algebraic morphism given by the action of the first groupoid upon the second and the anchor map. And how do we define, if we have this, how do we define an action from G to K and an anchor map? This anchor map rho sigma is from K to G0. Well, in fact, as groupoid, the groupoid K is isomorphic to this quotient, which is, if you take the H acts upon K, then you have this subset of the Cartesian product of pairs where the element of H can act upon the element of K. And then you put an equivalence relation, basically jumping the elements of H for the second by the action, and leaving only the unit of the target here in that part. Or if we H1 H2 K basically as H1 H2 K, basically you have those pairs equivalent. Then you quotient by that equivalence relation, and then this is what we could call the tensor. I'm not calling this tensor, but the balanced product between H and K, and this is isomorphic as groupoid with K. And then the anchor map is basically taking the class and taking the anchor map of the first. The anchor map row exists from H to the elements, the units of G. Then take the anchor of the first. And the action, the new action of G upon this K, which I will read like this, in the class of HK is G acting upon the first. Then basically it doesn't see anything on the second entry. And obviously by construction, it will be independent of the right action of the multiplication by K. Then and then this basically is the new discomposition between these two is a new algebraic morphism given by this.
Can I make a small comment on this, please?
Oh, okay.
Go ahead.
So another way to think about this, which may be a bit more kind of notationally intuitive, at least, is you have an actor of G on H, and then an algebraic morphism on G on H, and an algebraic morphism on H on K. So you have these two actions, and you want to know how to act from G, like from some G and G on some K and K. You take the corresponding unit in the middle in H. So you have this, your anchor map from K to H says that there is some unit in H which acts by doing nothing. And then you just act on the left by the G on that, and you get an element of H, which now can act by your second action on K, and this is the right thing. Essentially, you multiply by 1 in the middle, and you do the same analysis trick that we've all done since the beginning of time, which is multiplying by 1 sneakily.
Okay, thank you very much. This is quite clear. Huh? Okay, thank you, Jonathan, for this comment. Okay, then the considering this category, then there's a category I will call category of groupoid with algebraic morphisms. This is the category, and the bisection is the taking any groupoid, the inverse group of bisections, and then we can define for any algebraic morphism a morphism between the bisections. I didn't talk longer about how to express explicitly, but I will do it in the opposite direction, how to construct for Hopf algebroids this. But this is quite involved. But in fact, you can construct a functor from that category to the category of inverse semigroups. Okay, let us go to algebraic morphisms of commutative Hopf algebroids. Then I will more or less dualize that. And in fact, the new action which appear, it's more close to that what Jonathan told us about how to compose those maps. Let us see. Then you have a pair of a map from the base algebra. Then you have HA, you have KB, then you have H here, A here, K, then you have this anchor map goes in that direction, and instead of an action you have a left coaction of H upon K. Then this is and this coaction have to commute, delta commutes let's put on quote mark, commutes with the commultiplication on K on the right. The commultiplication thinking as a right coaction of K upon itself. Then these are the axioms. Basically, you are saying that each one was more or less giving the dual of what I said about groups. For example, here, uh, if we go from A to K uh, and then take the coaction, then it's natural to see that the the image will be only in the first entry, which is in A, and it is the target applied on the same A. This second basically is saying that it's co-unital, that coaction. Second and third basically is saying that this is indeed a coaction of H upon K on the left. And here, the fifth one is basically saying that the coaction commutes with the commultiplication on the right, as I said. And here is the compatibility. For example, if I go with the anchor map, then I apply the commultiplication, then it remains in the first entry. While if I apply the source map, then this comes from B, and apply the the coaction, then it remains in that part of K. This is more or less natural to expect, and these are duals or some of some um conditions given here, where these are basically dual of these conditions. Okay, let me see. And then commutative Hopf algebroids with algebraic morphism define a category. The identity morphism is simply taking the target map and the commultiplication. And the composition have this horrible form, but then this is basically what uh, Jonathan said, that you take the unit in the middle, and here you can see more or less that that is what we are doing here. You take apply the co-unit in the middle, and then put back into R prime. R prime goes to B, from B to L. R go from A to K, and then this R2 prime goes from A to L directly, taking the epsilon in the middle. You go from A to K, apply epsilon, then you go into B, and then apply R prime, and then this is more or less what happens here. And here, how do we define a coaction of H upon L? And this is the composition. And to prove that forms a category, it's a lot of work. And the semigroup of local bioattractions of a commutative Hopf algebroid defines a functor between the category of commutative Hopf algebroids with algebraic morphisms and inverse semigroup. I will take a hint of the proof of this. Let me see. Given a bioattraction, and an algebraic morphism there in the category of Hopf algebroid, one needs to define a new bioattraction of K, and then verify that this association gives a morphism of inverse semigroups. lots of work. And then how do we define the ideal J? The ideal J is given by this push out. You take the R composed with epsilon of K, and then the J basically is the ideal generated by the image of the ideal I when you go into B. This is the ideal who appears here. And the composition map beta, beta comes from K to B over J. And then you open with the coaction, apply alpha in the first, epsilon in the second. And this is basically, again, this is the alpha in I tensor over A B. This is the push out, and it's isomorphic to this. This is the isomorphism from these two forms of presenting the same push out. And then explicitly, beta of an element Y is basically given by this. This morphism appears by the construction of the push out, and then this is the expression of this biretraction beta. I will prove only small easy facts. For example, the composition with the source. Again, the delta of the source, the delta of the source of K of B is basically 1 of H tensor over B, no, tensor over A source K of B. This is what we are using here. And then this is 1, and this is the class of B in G. Then this is the projection. And beta composed with the anchor map gives this expression, which is useful for other proofs. The difficult part is to prove this. This is basically the hardest part of this proof, to prove that the beta composed with the target is surjective. Then one needs to verify that it's a morphism of semigroups, how to that from each of these you construct that by this recipe here, and then see that this is a morphism of inverse semigroup. Then, for example, if you take alpha I, alpha 1, alpha 2, I2, then if you apply this, then you go to the beta 1, J1, beta 2, J2. This is more or less involved as well to prove that part. Then mostly the biggest part of what we have written so far is to prove, to make the details of those proofs, which are in some points quite involved. But well, then let me go to the beginning of the seminar, when I said that there was an adjunction between groupoids with algebraic morphisms and inverse semigroups. From one side, you give the bisections, and the other side, you give the functor of germs of groupoid, the germ groupoid. What is how to construct this? I think my time is almost up. If
Well,
I take
you have minus 4 minutes left.
minus 4 minutes, okay. Well, then I think I don't know. I'm not going, because this I will only pass. It would be, but there are some attempts what I am going about our work, because there are some attempts to construct an analogous of the germ groupoid for the context of Hopf algebroids. This is still a work in progress. We didn't come to the final version of this germ groupoid. And there are some perspectives for them to obtain this correct adjunction from inverse semigroups and commutative Hopf algebroids with algebraic morphisms extend to the yes, we are going in another direction, which is extend to local setting. Some previous work of Xiao Han and Gianni Landi about the gauge transformation of Hopf-Galois extensions and biretractions of Edersmann-Schauenburg bialgebroid. We are doing things like that. Han and Lundy did for global gauge transformations and global biretractions of Edersmann-Schauenburg bialgebroid. And
but why only bialgebroid? It's a Hopf algebroid.
Not always, but we don't need that of the. We don't need.
I mean, Edersmann-Schauenburg bialgebroid is actually a Hopf algebroid in a Schauenburg sense. It's both the left Hopf and anti-left Hopf.
Yes, in fact, we use the inverse of canonical map instead of and yes, we are doing that direction with the inverse of canonical map. The last two things, general category, a general categorical context for bisections of inner groupoids in certain categories. Then, for example, even this work on commutative Hopf algebroid, it can be considered an inner groupoid in the opposite category of commutative algebras. Then, if we could embrace all these examples in one single categorical context, then it would unify several works existing in the literature. And the extension of this notion for the non-commutative context. And then I believe that this will involve, instead of inverse semigroups, something like quantum inverse semigroups. But this is only in the conjecture point. And thank you very much for your attention.
Muito obrigado.
I have a question. So, yeah, I mean, for bisection, we not only define on the Edersmann-Schauenburg algebra, we also define it on a very general Hopf algebra in non-commutative Hopf algebra. So I think maybe this can be also make it in your local picture. So that is
yes, this is because first we have to give up they being algebra morphism. They will be only or left or right module morphisms. Then this is the first modification we have to do. We don't know yet how to do this for local yet, but this is an attempt. We are going to that direction. We hope to obtain something like that. But then perhaps that star product, that convolution product, wouldn't give an inverse semigroup anymore, but a quantum inverse I hope to obtain a quantum inverse semigroup, an example of quantum inverse semigroup from this. But this is a hope only, a wishful thinking.
Okay, thank you very much.
Okay, anybody else? Ali, go ahead.
Okay.
Thank you very much for your very interesting talk. I have a question about the early part of your talk. Is there any terminology for a topological groupoid which doesn't admit any open bisection? You start your talk by definition of bisection as a subset U, for which for which it targets.
Yes, I see. Sorry, I see. Perhaps what, because when you have only a topological groupoid, and then only the continue, you have only to accept. First, you have perhaps the correct thing to do is take local sections of the source map, for example, and then, but perhaps you have many of them, but you cannot put, for example, if you take only the open,
Bisection, yes.
yeah, the open perhaps you can, certainly you don't have enough open sets to have a basis for example. This is certain, because then you end up into etal. I don't know any much further about general groupoids and how to deal with bisections in that so general context, in that general context.
Yes, I
But
see.
it's interesting to explore in that direction as well. I think.
Yes, I see. Because in classical case, for example, the groupoid, the fundamental groupoid of the topological space for typical topological space, one can find some open bisection. But as you say, it's not true that we have a lot of open bisection. So maybe it would be a good idea to consider this concept's existence or non-existence of open bisection.
Well,
Thank you for your explanation.
okay, thank you very much. Tomasz?
Okay. Tomek, go.
Okay, I have a question. This question is related to some comment I found on the chat, that your definition looks like a definition of a Zakrzewski morphism between groupoids.
Mm.
And
Yes, this is not new. In fact, in Alcides Bus' paper, they cited an older paper where that notion of algebraic morphism appeared first. It's not new thing.
So I have a question about this. These Zakrzewski morphisms were invented to allow to construct the functor from groupoids to convolution, to system algebras by the construction of the convolution algebra.
Mm-hmm.
So now you have a functor from groupoids to inverse semigroups. And I have a question, how these two functors are related. The functor of the convolution algebra of the groupoid and this inverse semigroup algebra.
Yes, in fact, for example, what I know is that when we started with the biretractions defined upon idempotents, then we ended up with the set of biretractions was a semigroup, but only a regular semigroup. But then we linearized it and then took the algebra of those biretractions, extending linearly that convolution product, and then we ended up with a quantum inverse semigroup according to that definition given in my first previous paper on quantum inverse semigroup. Then this is what and perhaps when we are going to the non-commutative case, when we have to give up the biretractions to be algebra maps, perhaps we have to go directly to the algebra of convolution and then prove directly that they are a quantum inverse semigroup. This is my expectation about this.
So I would be skeptical because this convolution algebra is something which generalizes the group algebra. But this algebra of functions on the group is a special case of your construction. So you are starting from this context. You're starting from this Hopf algebroid, which is a generalization of the algebra of regular functions on your topological or algebraic groupoid. So these two constructions regard arrows in this groupoid in a different manner. In one construction, this convolution algebra of the groupoid, this construction is covariant with respect to arrows, while in the second construction, it is contravariant with respect to arrows. So comparison between these two different constructions would invert this dependence on arrows, because you had to make something which depends contravariantly. You have to make it contravariant. So some duality must be involved relating these two constructions, which is maybe more mysterious. I cannot imagine what it could be. Of course, for quantum groups, in the sense of Voronovich, you can have this kind of Pontryagin kind of duality in terms of multiplicative unitaries, which are self-dual in a sense. So I would be happy to see in the comparison between these two constructions, this of Zakrzewski of this convolutional algebra, and this generalization of the algebra of regular functions on the groupoid, some kind of multiplicative unitary behind. But of course, it cannot be multiplicative unitary, because for groupoids you don't have this pentagonal identity which encodes the group structure. The groupoid structure is much more involved because of these non-trivial units. So this would be, I cannot even imagine what it should be. Some kind of parametrized multiplicative unitary, maybe in some bimodules instead of Hilbert spaces, maybe some Hilbert modules. I don't know. But it would be very interesting to marry this Zakrzewski's original approach, motivating these algebraic morphisms between groupoids, and this what you are now speaking about. Yeah.
I am going out of this seminar with a lot of things to think about, and perhaps thank you very much.
But by the way, Tomek, you just reminded me that at the conference which Gilles and I just attended, somebody gave a very succinct definition of a groupoid. So groupoid is simply a group with the identity crisis. Okay, Jonathan, fire.
Thank you.
Hi, thanks very much. This was a lovely talk. I had two questions. One of them, hopefully, is very quick. You had on, I think it's 2 slides ago, it's mentioned about Hopf algebroids being internal groupoids in a particular category. I just wanted to ask, is that all of these Hopf algebroids, or are all internal groupoids in this right category Hopf algebroids, or is it only a special subclass?
Let me see. For example, if I take let me put the category of commutative algebras, and then take the opposite, then this is a category where, and then if I take what is a Hopf algebroid there, basically you take 2 maps like these. Yes, you have epsilon and you have a delta from, and if you are in the opposite, then they can be, let me try to I will write this again, and I will write the arrows with another color. Then this source let me put star, but it's not in target star, and this is a unit, the epsilon star, and then the multiplication, which is delta star. It's because this is basically the you can see more or less as the set of composable pairs. Then you can have a multiplication. Then this seems like a groupoid inside this category. In this sense, I am saying that this is an inner groupoid in this category, but there are, for example, if with this categorical context, for example, group bisections on groupoids and in topological groupoids and would be treated in a unified way. This is basically what we are trying to do in that sense. But it is half of the things are done, but there's a lot of things to be done yet, not totally done. Okay, but you had two questions, you said.
Yeah, thanks. The other question is you've considered the category of groupoids with algebraic morphisms. Have you considered also possibly looking into what happens if you consider groupoid correspondences, which are a generalization of these?
Yes, this is very popular here as well in my group with Alcides. People they talk about, and I was very interested about correspondence, but yes, indeed, there should be some things to explore. For example, what should be correspondences in the context of algebroid? Perhaps a B, like a B comodule associated to two Hopf algebroids, and then to see what happens. Yes, and I never have done, but I think it's something worth to be done in that direction as well.
Okay, thanks very much. I guess I raised the question because my doctoral advisor was Ralf Meyer, so I'm
Yes.
also involved there.
Yeah.
But thank you very much.
Thank you.
Okay, let's wind it up. Anybody else? Okay, I don't see any other volunteers. So in this case, let us obrigado our speaker again. Muito obrigado. Thank you.
Thank you very much.
Let me stop recording.